Okay, so we have seen the non-homogeneous cases, how to convert them into homogeneous. We have also seen a second order differential equation to write it in a matrix form. And we have also tried solving a pair of first order linear differential equations. So what is the most important thing in this? So the most important thing in all the cases was to get to a general solution. Okay, so we haven't officially touched what a general solution is, but we have somewhat seen the idea of approaching it. Okay, so now we know how to find the eigenvalues and eigenvectors for the matrix method. And we also know how to convert the differential equation into the matrix method. So if you put all together, we can find the solution. Let's say, for example, I'm telling x of t is going to be my final solution. If it was of the form ax is equal to b. If it was of this form, then we have to find x, right? And over here, b would be x prime. So what we would do over here is, I've actually told you earlier that it's just a combination of e to the lambda t times the eigenvector. So one small change when you come to the general solution. So all you do is you're just going to put in a constant like how we did before in first order differential equation. So I'm going to put c1 e to the lambda 1 t times the corresponding eigenvector v1 plus c2 e to the lambda 2t times its corresponding eigenvector v2. Remember, this goes on until cn e to the lambda n t times vn. Okay, so I'm stopping here because it was only a 2 by 2 matrix, so we had only 2 eigenvectors. So that's why we stop here for the time. So c1 and c2 are just any constants. Okay, and something that's important over here is that the answer is a linear combination, right? So it's c1 times, so this one we can just tell it as, let's say, x1 of t, right? Or x1 vector, I'm just using the vector symbol, and let this be x2. Because since v1, v2 are all vectors, you'll be getting your answer as e raised to the power lambda 1t times v11 and e to the lambda 1t times v12. So you're gonna get like different combinations of this, right? Over here you'll get v21, v22, and so on. So if you look at it, it's actually just the linear combination. So that is what is the most important. So the solution is just a linear combination. And another thing which we have learned about linear combination is they should all be independent. It's very important that they're independent, because if they're dependent, then they can't be two different eigenvectors, because eigenvectors are defined in such a way that they are independent. So I gave you an example in one of the previous videos that v1 and v2, like just multiplying by -1. I'll just show it, bring it up to you again. So yeah, in this example, we multiplied it by -1. So remember, these two are dependent, so they still consider as the same eigenvector, and you can't say that this is a different eigenvector from that. Okay, so this is something important when we are looking at this. So it should be independent and it's a linear combination. And also we can extend the solution to an n by n matrix. So over there we come across this name called principle of superposition. So you've learned this before. So principle of superposition is basically when you have a 1 by 1, in this case a 1 by 1 matrix, or let's say a 2 by 2 matrix, and when you extend it to a 3 by 3 matrix, 4 by 4 matrix, 5 by 5 matrix, and so on up to an n by n matrix, the answer still forms the same pattern. Okay, so it is still a linear combination of e to the lambda t times its corresponding eigenvector. So by principle of superposition, we can say that x of t can just be sigma of ci e to the lambda I t times vi vector when I goes from 1 to n. So this is going to be the general solution for an n by n matrix, and we can change it as per the number of eigenvalues or the size of the matrix which we have. But according to the principle of superposition, this is going to be the general solution for the differential equations that are being solved to the matrix method. In the next video, I'm going to tell you to find the independence of the solution. Okay, thanks for watching.